Hello students, and today we're working on chapter 6.1 Introduction to Vectors from your Discovering Mathematics textbook. And if you look downwards at the corner of the screen, I will provide the page number. So you might like to prepare your notebook and your textbook as well as we go through the material today. Today we are going to do Introduction to Vectors. Okay, first and foremost, we talk about scalars and vectors. I will not spend too much time on this. For example, some quantities are called scalars. Scalars, we only have a magnitude. Simple things that are scalars are like the mass of a fish is 800 grams. The temperature of an office is 25 degrees Celsius. The speed of a car should not exceed 70 km per hour on a road. In this case, these quantities have no direction. They only have magnitudes, so hence they are scalars. However, if we look at other quantities like displacement, velocity and acceleration, and also force as well, they have both something known as magnitude and direction as well. So we call them vectors. For example, in the first example we have here is this: the metal sphere attached to the spring exerts a force of 25 newtons, and the force has a direction, and the force is acting downwards down here. Similarly, if I walk from home due east, okay, if you remember, north, south, east, and west. So if I walk due east, 800 meters from my home to school. So that itself has a magnitude and a direction as well. I will not dwell too much on this because you have already covered all of these concepts in physics itself. So in general, a scalar is a quantity that only has magnitude, while a vector is a quantity that has both magnitude and direction as well. How do we represent a vector? Since a vector has both magnitude and direction, it can be represented by a line. Okay, notice there's the word here that says directed line. Okay, the directed line segment is indicated by an arrow. It represents the direction of the vector. So if you take a look here at PQ, all right, so the vector starts from P, it ends at Q. And there is actually an arrow here to show the direction of the vector itself. The length of the line segment represents the magnitude of the vector. For example, a vector with a line like this, well, another vector with another line like this, we can say that the second vector has a greater magnitude than the first vector that I've just drawn in red, because I know that by visually looking at it, the second vector has a longer length as opposed to the first vector I have just drawn. Okay, if we look at two vectors here, first we have the line, the vector PQ, all right, and PQ is represented by the letter A. If you look at your textbook, you'll notice that the letter A is in bold. However, we are unable to write it in bold in the examination or in paper itself. So what we actually do is there is something called a squiggly line. All right, let me show you how to actually write it out for vectors with the squiggly line. Now, for example, in the first case down here, we have the vector PQ, and is known as the vector A. And we also have the vector, in this case, for the second case, let me use another color there. For second case, we have the vector RS, notice from R to S, and is represented by the vector B. Now, if you notice, there's something special there. It's different from what is written here. The difference between here and here is that I have this squiggly line here. The squiggly lines to tell people that there is actually a vector. Same thing, this is the vector B. The RS is represented by vector B. Similarly, B has to have a squiggly line as well. Okay, let's move on to the next portion. Now, we're looking at two vectors here, AB and CD. All right, AB can be found over here. This is AB. And this is CD going downward, so to speak, and that is vector CD. Now, there's something that we need to know is called a column vector. Okay, what is a column vector? If you look down here, they say that AB is represented as a column vector and CD is represented by a column vector as well. So how do you actually read or write down these column vectors? The top portion, right, shows the displacement, right, over here, the displacement, okay, on the x plane. All right, so basically it tells you whether the vector is going left or right. Okay, well, the bottom one tells you whether the vector is going up or down. So for example, if you remember, okay, for the plane x and y, going to the right is positive x, going to the left is negative x, going upwards is positive y, going downwards is negative y. So therefore, for column vector AB, it says they're moving 3 units towards x, positive x, so it's 3 units, right? Hence down there 3. So if you notice on this diagram, it moves 1, 2, and 3 units to the right. Then it's positive 4, so it moves upwards by 4 units, 1, 2, 3, and 4. So initially we started at A and then we end up at B. So this is the starting point, this is the ending point. We join them up and we show the direction, that is the vector AB. Similarly for CD, it can be represented as -1 and -3. So -1, okay, is moving towards the left on the horizontal plane. -3 will be moving downwards by 3 units on the vertical plane. So hence the vector, if this was a starting point and this is the ending point, the vector CD is represented down here like this as a column vector. CD is represented by -1 and -3. Next thing, we talk about the magnitudes of AB and CD. Basically, AB is a vector. Now, if we add in these two lines at the side, what we are asking for is the magnitude of the vector AB. Similarly, if we have a vector A, if I put two lines here, what I'm looking here for is the magnitude of vector A. Alright, so basically these two lines here will represent the magnitude. So how do we actually find the magnitude or the length of AB? Notice here, what does this form? It forms a right angle triangle. So if this is a right angle triangle, this is 3 units, this is 4 units. So for right angle triangles, we can apply Pythagoras' theorem to find the hypotenuse. This will be 3 square plus 4 square. We square root, we find the magnitude of vector AB is 5 units. Similarly for CD, this is -1, this was -3. Okay, so what we're interested in here is this. For the magnitude of vector CD, I just take the -1 and the -3. I square both of them. Just like Pythagoras' theorem, I square and then I square root it to get square root of 10 units. Hence, CD has a magnitude of 10 units. Therefore, the magnitude of any column vector x and y is given by square root of x squared plus y squared. Okay, this is basically how we derive the magnitude is found in the previous slide, and is the use of Pythagoras' theorem. Okay, now just some simple practice. If you want to try to pause the video, all right, and to try out these questions, please feel free to do so. If not, I will just carry on and explain how we get the column vectors for these 5 vectors. Okay, I shall first begin with vector KL. So for KL, all right, if you notice, we are moving 1, 2, 3. 3 units to the left. So that gives me positive or negative when we're moving to the left. It should be negative. Okay, so it's -3. So if I write, it should be -3. Then I need to move upwards by 1. If I move upwards, is it +1 or -1 unit? It is +1 unit. hence it's negative 3 and 1. So if I had to write down the answer, the vector KL represented as a column vector is negative 3 and 1. I look at column vector MN. Okay, for column vector MN is exactly the same as column vector KL. I'm moving 1 unit, 2 unit, 3 units to the left. That gives me negative 3. Then I move 1 unit upwards on the vertical plane. There's positive 1. Hence, we find that MN and KL have the exact same column vector. In fact, we'll learn a concept later to tell us that they are actually equal vectors because they have the same magnitude and the same direction. I'll now look at part C, where we'll look at PQ. For PQ, we start at P. Do we move left? Do we move right? No, we do not. Okay, so in this case, because we neither move left nor right, the value will be 0. Okay, so let me write that down, is 0. Then we move upwards by 2 units. 1 unit, 2 unit. Hence, if we are moving upwards by 2 units, is that positive 2 or negative 2? It should be positive 2. Part D, we're looking at vector RS. Okay, now some of you may do this, okay, for vector RS. If you start at R, you say, oh, I move down by 1 unit, so it's negative 1. Then I move to the right by 3 units, so it's positive 3. Then you will try to write down your answer as negative 1 and positive 3. Why is this incorrect? It's because you took the y value on top and the x value below. If you notice, for a column vector, it should always be the x displacement on the top and the y displacement at the bottom. Hence, negative 1 and 3 will be incorrect. So therefore, let me just erase this. And let's redo this portion here. So for RS, remember always to move on the horizontal plane first. So first for RS, I will move forward by 1, 2, and 3 units to the right, and move 1 unit downwards. So 3 units to the right is positive 3. 1 unit to the downwards is negative 1. Hence, the vector RS is 3, negative 1. Finally, we have the vector QQ. Alright, for the vector QQ itself, notice that it doesn't move left, neither does it move right. We do not move up, we also do not move down. In fact, there is no movement, no displacement at all. Hence, the vector QQ can simply be represented by 0 and 0. And there we have, try it 1. Okay, now we are on page 157 of your textbook. We are going to talk about equal vectors. So as I briefly mentioned in the previous slide, two vectors are equal if they have the same magnitude and are in the same direction. So I give you the example of AB and CD now. For AB, they both have the same length, alright, and they also both have the same direction. Hence, having the same length means it's the same magnitude, and they also have the same direction. Hence, the vectors are equal if they have the same magnitude and are in the same direction. Then now, okay, there's this line here. So they say that two vectors are equal only if the x and x over here are the values are exactly the same, and the y and y values are exactly the same. Then we can say that they are equal vectors. If I bring you back to the previous slide, if you notice just now for KL, MN, KL is negative 3 and 1, MN is negative 3 and 1. So in this case, they will have the exact same magnitude, the exact same direction. So in this case, KL is exactly equals to MN. And what this actually means for us is that they are actually equal vectors. Okay, now I give you another example. If you look right at this case, AB and HG, all right, they have the exact same length. Means that they have the same magnitude. However, you notice that AB is going this way, while H3 is going the other way. So in this case, even though they have the same magnitude, but they occur in opposite directions. So GH is actually the negative vector of AB. So hence, if I were to write it down, GH is equals to negative of AB because it is actually going the other way. Now I'm going to look at page 158 and we will look at try it too. Okay, try it too. First and foremost, they will talk about the vector B. So if I were to rewrite the question, the vector B is equals to negative 3 and 8. Notice that I purposely rewrote the question so that you take note of the squiggly line here to denote that B is a vector. The first part here is this. They want us to find the magnitude of vector B. So in this case, what I'll do is this. I'll say that the magnitude of vector B is equals to negative 3 square plus 8 square. I square root this. It gives me 8.54 units. And this is correct to 3 significant figures. Then now, they said that they want the negative of vector B. So what I can do here is the negative of vector B is I just put in the negative sign outside. So where is the negative sign here? Negative sign here. So it works the same way as matrices. You just multiply the negative sign in. What we get is 3 and negative 8. Now, if I were to find the magnitude of the negative B, what I'll get applying the formula is 3 square plus negative 8 square. I square root. You input this into the calculator, you find that you get the exact same value of 8.54 units as well. So this is to draw a point. Note vector B has a magnitude of 8.54 units. Vector negative B has a magnitude of 8.54 units as well. So they have the same magnitude, but the only difference is because of the negative symbol, they will be going in different directions. Right, now I look at part D itself. Alright, they say that negative B is equals to P minus Q and 4Q. Please be careful. All these inside here are variables. They are not vectors, so do not get confused over here. So I'll start to equate and say this. 3, negative 8. They say the equivalent is P minus Q and 4Q. So what I'll have to do here is this. I will believe that I will get, okay, let me just use a highlighter so that you won't get confused here. 3 is equals to P minus Q. Negative 8 is equals to 4Q. So if I start solving, I will say that 4Q is equals to negative 8. Q is equals to negative 2. So I have one answer. Then I will do the next portion where P minus Q is equals to 3. Since Q is equals to negative 2. Oops, slight error there. So P minus negative 2 is equals to 3. Therefore, P itself is equals to 1. So P equals to 1 and Q is equals to negative 2. Alright, I'm now on page 159. I'm looking at try it 3. Okay, so D is H negative 5. The vector D is H and negative 5. If the magnitude of vector D is 13, find the possible values of H. So just let me write it down. So the first part that I'm going to do is this. I'm going to translate this into an equation. So I'll say that the magnitude of vector D is equals to 13. So what is the magnitude of vector D? I will get those values from here and here. So I'll say that H square plus negative 5 square root is equals to 13. Now, how do we get rid of the square root? That's right, we shall square both sides of the equation. So once we do that, what we'll get is h squared plus 25 is equals to 169. Then h squared is equals to 144. Now be careful here. When you square root both sides to get rid of the square, here and here, excuse me, what you get is h equals to 12 or negative 12. Do not forget that whenever you square root a number, there's both a positive root and a negative root as well. And that is it for try it. Now we talk about try it for. Try it for, we see that PQRS is a rectangle. So we have to determine and explain whether the vector PQ is equals to the vector RS. Okay, PQ and RS have the same magnitude. Why? They have the same length. However, if you notice, PQ is going towards the right and RS is going towards the left. So in this case, even though they're the same magnitude, they are going in they are going in opposite directions. Hence, for the first one, the PQ, vector PQ, is not equals to the vector RS, as they have different directions. Okay, now we have to determine whether the vector QR is equals to vector PS. Same thing, you notice both of them have the same magnitude, but in this case, different from part A, they also have the same direction. So two vectors are equal if they have the same magnitude and the same direction. In this case, I will say that the vector QR is indeed equals to the vector PS, as they have the same magnitude and direction. And just for effects, I will highlight the 2 points there. Same magnitude, same direction. Okay, now we're going to move it on to try it 5. Alright, for try it 5, the diagram AB represents the velocity u. Find the magnitude of the vector u. Okay, just to remind you all that for vectors, you have to have the curly line. Okay, so now, how will I find this? Basically, I will express the vector u as a column vector first. So if you remember, column vectors, in this case, we go by the x direction. 1, 2, 3, 4. This is negative 4. And it's going downwards by 2 units, and it's negative 2. Hence, I can write down as column vector. Vector u is equals to negative 4 and negative 2. Now, if I want to find the magnitude of vector u, what I do here is this. The magnitude of vector u is equals to negative 4 square plus negative 2 square root. We quickly compute that is equals to square root of 20 units. Okay, but be very careful here. They say here that 1 unit represents 5 meters per second. So this one, what we have to do here is to multiply it by 5. Hence, alright, I'll say this, since 1 unit represents 5 meters per second, the magnitude of vector u is equals to 5 times square root of 20. So that will give me 22.4 meters per second, correct to 3 significant figures. Now, for part B, they say describe the direction of u using bearings. If you remember, bearings is actually a work from secondary 4. But now, let me just show you. So basically, what they will want from the diagram is this, I draw. So for bearings, we need to have the north line. And then what is the bearing that we're looking for? It goes clockwise. So this is the angle. This is the angle that we need to find for the bearing. Okay, first and foremost, let me focus you onto the diagram itself. So to find this angle, though in red, it may not be that simple. So what we actually do here is this. I actually will draw a few more lines to help me. I will say that this and this, okay, this actually forms a right angle triangle. So I am attempting to find this angle in purple. I call it theta. So if you notice, what can we apply for right angle triangles? We can actually apply trigonometry ratios, to, ka, and so. So if you go and count, this actually is 2 units, this is 4 units. So with respect to this angle here, this is the opposite, this is the adjacent. Opposite and adjacent, what can we apply? Okay, we can actually apply tangent. So now for part B, what I'm going to do here is this. I will say for part B, I will say tangent theta is equals to opposite over adjacent, 2 over 4. I take the inverse tangent of 2 over 4, I find that is 26.57 degrees. Now, don't forget that this is not the bearing yet. So what I do here is this. If you look here to get this angle here in red, you take note that from here to here, this is 270 degrees. So what I do is I'll take the 270 degrees, I minus away this angle theta, which I found to be 26.57. It will give me the bearing, which is 243.4 degrees. So let me just do the working there. I will say that the bearing of the vector u is equals to 270 minus 26.57 degrees, and I will get 243.4 degrees. And that is it for try it 5. Okay, now I'll work on some examples from exercise 6.1 that can be found on page 164 of your textbooks. So you might like to use your textbooks as I go through this. So for question 6 itself, we'll talk about magnitude. So I'll start with this. The magnitude of the vector, okay, of vector is equals to 13 units. And that is given down here. So what I can say is this. Let me set up the equation. I will say that 12 square plus m square, I take the square root of that, is equals to 13. To get rid of the square root, what I'll do is I will square the left hand side, I will square the right hand side as well. So what that gives me is 144 plus m square is equals to 169. Hence, m square is equals to 169 minus 144. It gives me 25. Hence, the value of m is equals to 5. Some of you may forget that there is also a negative root. So, m is equals to 5 or negative 5. Okay, this will be the last example I give for this portion before you can move on to your homework itself. So now we are talking about translation. So basically, what is translation? Okay, it's not like we're translating English to Mandarin. Okay, translation works like this. Let me just give you a simple example. Let me just draw a shape out here. Okay, let me draw something out in purple. Okay, so basically translation is this. So there's this purple triangle I have over here. I select the purple triangle. If I translate the triangle, it simply means I move the triangle. Nothing changes, the size doesn't change, the angles don't change. The triangle remains exactly the same. So you're just moving it. So another way of saying translation is that we are moving the object. So in this case, I'll translate the triangle up here. I'll translate the triangle down here. I'll translate the triangle down here. Notice that nothing changes, it's just that the position of the triangle changes. Alright, okay, now let me just erase this. So now they're asking you, use a column vector to represent the translation of figure A to figure B. So basically, when we look at translation, we can actually look at a single point by itself to see how the figure translates. So now, what I'm going to do here is this. Okay, let me choose a nicer color. I will use orange. Alright, so maybe we pick a point. Let me pick this point orange, and this point in red. So basically, when I translate A to B, what is happening here is the point, okay, the point in orange and the point in pink, they're the same points except they move. So if I just notice or I try to understand how this one single point moves from here to here, I can get the column vector. So in this case, what happens here is this, all right, it moves 1, 2 here. Okay, but be very careful. Notice that every 5 squares will represent 2 units. So therefore, from orange to red is 2 units, 4 units, and then it moves upward again by 2 units. Why 2 units? From 6 to 8 is 2 units. So hence for the translation for A to B, what we have here is this. Okay, we have the column vector is 4 and 2. Okay, now I move back to the diagram itself. So we are trying to use the column vector to represent translation of figure B to figure C. Same thing here, we just pick a point, okay, that's convenient. Let me pick this point and I pick this point. They are the same point, okay. So basically what happens is that it will move, okay, the orange point will translate to the red point. So that's how the translation works. So same thing here, we start counting, okay, on the x direction first. -2, -4, -6, -8, -10, -12. On the y direction, we move down by 2 units, so it's -2. So what we have here is -12 and -2. Okay, why don't you just take a moment, okay, pause the video and try to work out the translation from figure C to figure A. And then you can unpause the video to see if your answer is correct or not. Okay, for figure C to figure A, what happens here is this. Okay, I will choose a point as convenient. Let's mix it up a bit. I choose a different point now. I choose this corner over here and I choose this corner over here. So basically the translation, all right, will work like this. So I will see here is 2, 4, 6, 8. So does it move up and down? It doesn't, okay? So therefore, there's only a translation in the x direction. So hence, for part C, the required vector that we need is, oops, wrong color. And the required vector that we need is 8 and 0. All right, and this concludes, right, the first chapter 6.1 on vectors. So you can actually move on to class kick to do